Introduction to TensorFlow. TensorFlow is an open-source library for machine learning and deep learning. It is created by Google and supports building and training neural networks. TensorFlow is used in real-world projects like image recognition, natural language processing, and recommendation systems. You can use TensorFlow to create models that learn from data and make predictions. Running the cell now. Let us install and import TensorFlow. In Windows, use pip install TensorFlow in the terminal if it is not already installed. This line disables warning messages. This imports TensorFlow so we can use it in our code. Running the cell now. This code imports TensorFlow, the key library for building and training machine learning models, and suppresses user warnings to keep the output clean. Though there's no visible output here, this step sets up the essential tools needed to create and run neural networks in the upcoming lessons. Notice how TensorFlow is imported with a simple alias tf, which is the standard convention you'll see throughout TensorFlow projects. Core concepts of TensorFlow. TensorFlow works with tensors, which are multidimensional arrays. Models in TensorFlow are built using layers and operations. Training involves feeding data and adjusting model weights. TensorFlow can run on CPUs and GPUs. Running the cell now. We will create our first tensor which holds a single value. This defines a constant tensor with the value 5. We print the tensor. It shows the value and type. Running the cell now. This output shows a scalar tensor with the value 5, a shape of, indicating 0 dimensions, and an integer data type. It highlights the core TensorFlow concept that even single values are represented as tensors, which are the fundamental data structures in TensorFlow models and operations. Let us make a tensor with several values. This tensor contains a list of numbers. We print the tensor to see its contents. Running the cell now. This output shows a one-dimensional tensor with 4 integer values, as created by the tf.constant function. Notice the shape, 4, indicating a vector of length 4, which highlights how TensorFlow represents multidimensional arrays. This is fundamental for understanding how data is structured and processed in TensorFlow models. We can find out the shape and data type of our tensor. This prints the shape. It tells us how many elements there are. This prints the data type of the tensor. Running the cell now. This output shows that the tensor B is a one-dimensional array with 4 elements, and its data type is 32-bit integer. Noticing the shape, 4, confirms how TensorFlow represents tensor dimensions, which is fundamental when building and manipulating models. Understanding these properties helps ensure that tensors are correctly structured for layer operations and training. Beginner example, arithmetic with tensors. You can do math like addition and multiplication with TensorFlow tensors. Running the cell now. Let us do addition using 2 tensors. This tensor has some values. This tensor has some other values. We add them together and store the result. We print the result tensor. Running the cell now. Here, the output shows the result of adding 2 tensors element y's. Notice that each element in x is increased by the corresponding element in y, producing a new tensor with the same shape, 3. This demonstrates how TensorFlow allows straightforward arithmetic operations on tensors, keeping their shape and type consistent. Now let us multiply 2 tensors. This tensor is the first set of values. This tensor is the second set of values. We multiply the tensors. This multiplies each pair of values. Running the cell now. Here, we multiplied 2 tensors element y's, which means each position in tensor m is multiplied by the corresponding position in tensor n. Notice the resulting tensor has the same shape, 3 elements, and shows the products 10, 18, 28, illustrating how TensorFlow handles arithmetic operations on tensors element by element. TensorFlow tensors can be converted to NumPy arrays. This converts tensor B to a NumPy array. We print the array. Running the cell now. Here, converting the TensorFlow tensor B to a NumPy array using .NumPy gives us a familiar array format, 1, 2, 3, 4. This shows how tensors can easily be transformed for use with other Python libraries, reinforcing that tensors hold numerical data just like arrays but with extra functionality for machine learning. Beginner example, variables. tf. A variable is used when you want to change the value of a tensor. Running the cell now. Let us create a modifiable tensor. This variable can change its values. We assign new values to the variable. We print it to see the new values. Running the cell now. This output shows a TensorFlow variable initially holding the values 10, 20, 30, which is then updated to 40, 50, 60 using a sign. Notice the shape and data type stay the same, highlighting that tf variable allows us to change tensor values while keeping their structure intact. This demonstrates the key use of variables in managing mutable state within TensorFlow. Beginner example, basic operations. You can use TensorFlow functions for math operations, such as tf.add or tf.multiply. Running the cell now. Let us use tf.add to add numbers. We print the result using NumPy for easy reading. Now we will multiply using tf.multiply. We print the multiplication result. Running the cell now. Here, the output shows the results of basic math operations using TensorFlow functions. tf.add adds two numbers, and tf.multiply multiplies them. Notice how the results, 8 and 42, match the expected sums and products, demonstrating how TensorFlow handles simple arithmetic in a way similar to regular Python operations. Intermediate example, creating a simple neural network model. Keras, inside TensorFlow, helps make models easily. We will build a model with one input and one output. Running the cell now. We import Keras and its layers. We get the layers module for building models. This creates a simple neural network model. This model has just one layer with a single output, dense. This prints a summary of our model. Running the cell now. This model summary shows a simple neural network with one dense layer having a single input and output, matching our design. Notice the output shape none, 1, where none stands for the flexible batch size, and the two parameters correspond to one weight and one bias, which are both trainable. This confirms we've successfully created a minimal model ready for training on scalar input-output pairs. We set up the model for training. This uses stochastic gradient descent and mean squared error loss. Running the cell now. Here, we've compiled our simple neural network model using the SGD optimizer and mean squared error loss function. Notice there's no textual output because compile just configures the model's learning process without running it. This step is crucial as it sets how the model will update during training, aligning with our goal to build and train a straightforward input-to-output network. We will make some example data for training. This is an array of input values. This is the output for each input value. It is just input times 2. Running the cell now. This code defines the training data for our simple neural network, where xs represents inputs and ys the corresponding outputs, showing a clear linear relationship. Each output is twice the input. Although there's no printed output here, setting up these tensors is crucial because the model will learn to map inputs to outputs based on this data pattern. This step prepares the foundation for training the model to understand and predict this relationship. We will train our simple model with the data. This line trains, the model for 400 epochs. Running the cell now. This output confirms that the model training process has completed and returned a history object, which stores details about the training like loss values over epochs. Although no metrics are printed here, the focus is on successfully running the training loop for 400 epochs, demonstrating how Keras simplifies model fitting with just one line of code. This sets the stage for evaluating model performance in the next steps. This comment explains that we are about to make a prediction using the model. We import NumPy so we can create numeric arrays for the model input. This line runs the model using the input value 7 and prints the predicted output. Running the cell now. This output shows the model's prediction when we input the value 7, producing approximately 13.89 as the output. Notice how the model generates a single floating point number wrapped in double brackets, reflecting its expectation of a 2D input and output shape. This confirms our simple neural network is working, mapping one input to one output as intended. Intermediate example, loading data with TensorFlow. Use tf.data.Dataset to manage data batches. We will make a dataset from Tensors. Running the cell now. We create a dataset from two lists. For each feature and label pair in the dataset, we will print them. This line prints the feature and label values as numbers. Running the cell now. Here, the output shows how tf.data.Dataset.from_tensor_slices creates pairs of features and labels by slicing the input tensor's element-wise. Notice that each feature from the first tensor is paired with the corresponding label from the second tensor, illustrating how TensorFlow organizes data into manageable batches for training. This confirms our dataset is correctly structured for iteration in model pipelines. Intermediate example, saving and loading models. You can save your trained model to a file. You can also load it later to reuse without retraining. Running the cell now. We will save our current model to a folder called my_model. This line loads the model back from the folder. We print a message so we know it worked. Running the cell now. This output confirms that the model was saved to a file and then loaded back correctly, demonstrating the ability to reuse a trained model without retraining. Notice how the message verifies successful saving and loading, reinforcing the practical workflow of preserving your work for future use. Advanced example, custom layers. You can create your own custom layers by subclassing tf.Keras.layers layer. Running the cell now. We define a custom layer that triples the input values. This is the layer constructor. We call the parent class initializer. This function defines what happens to inputs. It multiplies them by 3. We build a model with our custom layer. We run the model on input 2.0. We print the output, which should be 6.0. Running the cell now. This output shows that our custom layer successfully multiplies the input by 3, as seen with the input 2.0 producing an output of 6.0. Notice the shape remains the same, 2.0 to 6.0, demonstrating how the custom call method manipulates data while preserving its tensor structure. This confirms the intent of subclassing tf.Keras.layers at layer to define tailored layer behavior in a model. Advanced example, training with callbacks. Callbacks let you stop training early or save models automatically. Running the cell now. We make a callback to stop training when loss stops getting better. We train the model again, now with the callback. We print a message when training stops. Running the cell now. This output confirms that training has completed, likely before the full 50 epochs due to the early stopping callback monitoring the loss. Notice how error stopping helps save time by halting training once the loss stops improving for 2 consecutive epochs, demonstrating efficient training management in advanced workflows. Error handling and debugging in TensorFlow. Errors may happen if shapes do not match or types are incorrect. Use try and except to catch errors. Running the cell now. We use try and except to catch TensorFlow errors. Here we try to add tensors with different shapes. If there is an error, we print what happened. We print the error message. Running the cell now. The code attempts to add tensors with incompatible shapes, which normally raises an error. However, because the operation is wrapped in a try-except block, the error is caught and prevents the program from crashing, leading to no output being printed. This demonstrates how try-except blocks help gracefully handle shape mismatch errors in TensorFlow. Best practices and common patterns. Always use tf.constant for data you do not want to change. Use tf, a variable for values you will update. Use clear names for layers and variables. Save your models after training them. Use callbacks for more control during training. Running the cell now. Mini-project, build and use a model. We will build a model to learn y equals 3 times x plus 1. We will train it and make predictions. Running the cell now. We define a new neural network model for our mini-project. We compile the model with optimizer and loss function. These are our training x values. These are our y values, which follow the rule y equals 3 times x plus 1. We train our model for 500 epochs. We ask the model to predict the value of y for x equal to 10. We print the predicted result. Running the cell now. This output shows the model's prediction for x equals 10 after training on the data following the function y equals 3x plus 1. Notice how the predicted y value, (31), is very close to the true value, 3 times 10 plus 1 is equal to 31, demonstrating that the model has successfully learned the underlying linear relationship. This confirms the training process effectively minimized error and fitted the intended function. Now it is your turn. Type a number and let us see what the model predicts. We ask the user to enter a value for x. The model predicts y using the value entered. We print what the model predicted. Running the cell now. This output shows the model making a prediction for the input value x equals 5.0, resulting in y equals 16.00. Notice how the predicted value closely follows the intended linear relationship y equals 3 asterisk x plus 1, confirming the model has learned the pattern from training. This demonstrates how the code takes a user input, feeds it to the trained model, and outputs a prediction in real time. Thank you and next steps. You now know the basics of TensorFlow. Keep trying new examples for practice. Subscribe for more tutorials. Leave a comment if you want to see more. Running the cell now.